Hi everyone, welcome to the next lecture. In this lecture, we will discuss about bit manipulation. So bits are very important part of our system for storage purpose. So computer understands only low level language, that is machine language. So it is a combination of zero ones only. Okay, binaries, we call them binaries. So we'll study about bit manipulation. For that, let's take one example. Okay, let's see in our system, we have 1 TB of storage. Usually we do have, right? So 1 TB of storage is nothing but equivalent to 1024 GB. Okay, and 1 GB is equivalent to 1024 MB, correct? And 1 MB is equivalent to 1024 KB, correct? And 1 KB is equivalent to 1024 bytes, correct? This is bytes. And 1 byte is equivalent to 8 bits. Okay, so we started with TB. Okay, and we went down till bits. So bit is a smallest unit of storage. Bit is a smallest unit of storage. Okay, smallest unit of storage. And why is it important to learn bit manipulation? Why is it important to know about bits? Because in our system we have 1 TB of storage, but there are a lot of appliances, there are a lot of components which is still working on KB, which is still working on bits. Okay, which is still working on bytes, which is still working on MBs. So in hardware industry we have a lot of components. So to work with them, we need to have a good understanding of bits. Okay, so that's why bits is important. In semiconductor companies, they will grill you on bit manipulation. Okay, in any semiconductor company, if you give interview, they will grill you on bit manipulation. Okay, they will know how well you know the basics of bit manipulation, how well you know C, C++, how well you know OS concepts. So they ask you very basic concepts. Okay, so we need to know the basics. We need to know the basics. Okay, so let's start. So in our system we have studied about representation system. Okay, representation system. Okay, number representation system. So we usually have four types of number representation systems. Okay, first we have binary. Okay, as the name suggests, binary means two. So we have 0 or 1. Okay, second octal. Octal, as the name suggests, 8. So we have 8 values. Okay, we can have 8 values. So it will be from 0 to 7. Okay, we will study about it, right? Next, we have decimal number representation system. Okay, here we have 10 values, which we usually use. Okay, which we use in coding or anything. So we have 0 to 9. Then we have hexadecimal. Okay, we have hexadecimal. So in hexadecimal, we have 16. Okay, hexadecimal 6, 10. That means 16. So we have 0 to 9 and then A to count the next values A, B, C, D, E, F. Okay, so A to F. Now, how you can find whether the number given is in binary or octal or decimal or hexadecimal? So usually we use decimal, right? Whenever we store like int a equals to 10, 20, 30, whatever we store, we use generally decimal number system. Okay. So how to find whether a number is binary or octal or decimal or hexadecimal? So for octal, we have prefix 0. Okay. And for hexadecimal, we have prefix 0x. So if a number starts with 0x, something like this, that means it is in hexadecimal form. So there you can find A, B, C, D, E, F like this also. Okay. Along with numbers, you can find the alphabet also in hexadecimal. In octal, we have from 0 to 7 only. Okay. Because octal means 8. So 8 values can be there. Now, let's start with binary only. Okay. Let's start with binary only. So in binary, we have two values. Okay, we can have two values, either 0 or 1. So 0 usually means false, okay, or off. 1 usually means one, sorry, true or on, like this. Okay, so binary numbers can be used for signaling. Okay, so if you want to turn on or turn off the switch, you can use binary. We have two choices, 0 or 1. Okay, what we have more choices, we have more options. So we can look for octal, okay, or decimal. Okay, so in our program, what we used to do, we used to take something like int a equals to 5. Okay, so we usually use decimal number system. Okay, we use decimal number system. Now in integer, what we usually do, we can take negative numbers also. Okay, so let's say if I store -5, we can store this also, right, in integer. So by default in C++, this int is nothing but signed. There are two types of values. Okay, there are two types of data types, signed or unsigned. What does it means? Signed means we can have both types of values. Okay, positive as well as negative also. But in unsigned means we don't have negative value. Okay, so we will only have positive values. Okay, along with 0 also, from 0 to any positive value. Okay, in the range. But signed can have positive as well as negative. So by default in our C++, in C or C++, we consider it as signed only. Okay, because it can store positive as well as negative also. Now we store decimal values, but if I want to convert it in binary, how we can do that? If I want to convert it in binary, so let's say I want to convert decimal. We understand decimal, right? But we need to understand how we can convert it in binary. So let's say I want to convert decimal to binary. Okay, so first of all, let's take 2 bits. Let's say we have 2 bits. How many numbers I can store it in 2 bits? Okay, as of now, I can consider only unsigned. Okay, unsigned means I'm considering only positive values. Okay, now how many values I can store it in 2 bits? So 2 bits means we have, let's say this is 1 bit and this is another bit. Okay, so we can have 4 combination, right? 2 is to power 2, 4 combinations. So what we can do, we can either put this, or I can take this, or I can take this, or I can take this. Okay, these can be the possible values taking 2 bits. Okay, now how to represent them in decimal? Okay, how to represent them in decimal? So if we have any binary number, let's say we have 1010, so what we generally used to do, so we start from 2 is to power 0, 2 is to power 1, 2 is to power 2, 2 is to power 3. Okay, and we multiply with this digit. Okay, and we keep add them. Okay, so this will be 1, this will be, so if I write, this will be 2 is to power 3 into this value, plus 2 is to power 2 into this value, plus 2 is to power 1 into this value, plus 2 is to power 0 into this value. So this will result me what? This will be 8 plus anything multiply with 0, 0, plus this will be 2, plus this will be 0. Okay, so this will be 8 plus 2, 10. So this is 10. In decimal, it will be 10. Okay, that's how we convert binary to decimal. Correct? So simply what you can do, you can write here only 2 is to power 0, 2 is to power 1, 2 is to power 2, 2 is to power 3. Okay, and whatever value is 1, just multiply with them and add them. Okay, so 2 is to power 3 plus 2 is to power 1. This will be nothing but 10. Okay, so that's how we can convert binary into decimal. Now, if we want to convert decimal into binary, how we can convert that? So let's say we have given 10. Okay, so just do it. 2 divided by 5. What will be the remainder? Write remainder here. So remainder will be 0. Okay, 2 into 2, 4. Remainder will be 1. 2 into 1, 2. Remainder will be 0. Okay, and at the end, this will be 1. So write 1. Okay, and just write it from lower to upper. Okay, write it from bottom to top. So it is 1 0 1 0. It is 1 0 1 0. Okay, from bottom to top. So that's how we can convert decimal to binary. Okay, from binary to decimal, just multiply every number with 2. Okay, 2 is to power 0 1 2. Keep increasing the power. And for decimal, and for converting decimal to binary, just take a LCM. Okay, just take the remainder from bottom to top. Now this is our binary. Let's say this is our binary number. So in binary number, we call this as LSB, least significant bit, and this we called as MSB, most significant bit. Okay, so on the left side we have most significant bit, and on the right side we have least significant bit. Okay, just remember this term, MSB and LSB. Okay, we will use it further. So till now what we have done, we have taken a decimal number, we have converted into binary, and we have taken a binary number and converted into decimal. So I hope you understood it. Okay, what we do, we generally take bottom to top. Okay, and write it here. Now the binary equivalent of 10 was 1010. Okay, so how many bits required, to store 10? So we have 1 2 3 4. 4 bits are required to store 10. Okay, 4 bits are required to store 10. So if I want to know, using 3 bits, how many numbers I can store? Okay, unsigned, how many unsigned number I can store? So what will be the possible combinations? Okay, we can have 000, 001, 010. Okay, so these are the all possible combinations. Okay, and using them, what are the all decimal equivalent? So the decimal equivalent of them will be, this will be 0. Okay, this will be 1, this will be 2, this will be 3 4 5 6 7. Okay, so using 3 bits I can store decimal value from 0 to 7. Okay, same using 4 bits, how many numbers I can store? Okay, I can simply take 2 raised to power 4. This is nothing but 16. Okay, and if I'm starting from 0, so I can store 0 to 15. If I want to know, using 5 bits, how many numbers I can store, I can write 2 is to power 5. It is equivalent to 32. That means from 0 to 31. Okay, that we can understand, right? So using n bits, I can store 2 is to power n numbers. Okay, 2 is to power n numbers from 0 to 2 raised to power n minus 1. Okay, so just note it down. Using n bits, we can store 2 raised to power n numbers from 0 to 2 raised to power n minus 1. Okay, and I'm talking about unsigned data. I'm talking about unsigned. Okay, so I hope you understood till now. Okay, I have done very basic concept. Till now. Now, I want to take a big example. Okay, I want to take 4 bits. And what will be the all possible combinations using 4 bits? Okay, so let me write all possible combinations using 4 bits. So it can be, so these are all possible combinations using 4 bits. Okay, these are all possible combinations using 4 bits. Now how we can store it using different data types? Okay, so let's see. So if I have unsigned data, okay, if I store it in unsigned data, so it will be 0 1 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, if I want to store it in unsigned data, then these are my values from 0 to 15. Now, if I want to store it in signed data, okay, if I want to store it in signed data type, then what will happen? What will happen? See, signed data means positive as well as negative. Okay, positive as well as negative. Unsigned means only positive values. So if I'm storing both positive and negative values, that means we will have half of the values positive and half of the values negative. Okay, we will have half positive values and half negative values. So how we can store them? Okay, how we can store them? So there can be multiple ways to store signed data. Okay, there can be multiple ways to store signed data. Let's start with a very basic one. So we want to, till now in unsigned, we want to store all positive numbers. But in signed data, we want to store positive as well as negative. Okay, and I want to store equally, half positive and half negative, almost equally. Okay, so what I can do, I can divide it. Okay, I can divide this into two parts. So if I divide this will be my half part and this will be my another half. Correct? Now, what I can do, I can store it in positive or negative way using bits. Okay, using bits. So I already told you that this is our MSB. Okay, most significant bit. And this is our LSB, least significant bit. So by seeing MSB, can I do something? By seeing MSB, can I do something? Okay, we have the zeros, we have the ones here. Okay, so if I divide on the basis of MSB, can we do that? So my idea is, if my MSB is 0, I will store positive values. Okay, and if my MSB is 1, I will store negative values. Okay, I will store negative values. Correct? So how we can store positive and negative values? So what I can do, I can just take these bits. Okay, my MSB bits will be used for sign only. Okay, and I will take actual values using these bits. Okay, so let's start taking this. So from here to here, all values will be same. This will be 0, this will be 1, 2, 3, 4, 5, 6, 7. Okay, but from here from here my values, my sign will be changed. Okay, so if you don't consider this, these will be our actual values. Okay, these will be our actual values using negative sign. So let's write it. Just see only this, just see only these three bits. Okay, so my value will be 0, 1, 2, 3, 4, 5, 6, 7. Okay, and please use the negative sign also. So this will be -1, -2, -3, -4, -5, -6, -7. Okay, so this can be our one representation. Okay, but the problem with this representation is we have here 1 0, we have here 1 0. Okay, these values, okay, fine. These values, fine. But we have two zeros. Okay, we have two zeros. So in any range, let's say I'm starting from negative to positive, so we'll have only 1 0, right? From negative to positive, if I'm drawing on number line, we'll only have 1 0. But here we have two zeros. Okay, so this will not in use. Okay, we don't use them. Not in use, we don't use them. Okay, we need something better. We need something better. So there is one more way. Okay, there is one more way which we called 1's complement. If I store it in 1's complement form. So before storing in 1's complement form, let me tell you what is 1's complement. Okay, so it's very easy. Let me tell you what is 1's complement. So let's say you have given a number in binary form. Let's say you have given this only. Okay, this is nothing but 10. This is 8. This is 2. So it is 10 in decimal. Okay, so if I take this, and I want to find 1's complement of it. So 1's complement is nothing but inversion of bits. Okay, it is nothing but inversion of bits. Simply inversion of bits. Whatever bits given to you, just invert them. So in binary we only have 0 and 1. So wherever we have 0, just replace with 1, and wherever we have 1, just replace it with 0. Okay, so after inversion, so replace 0 will be replaced by 1, 1 will be replaced by 0, 0 will be replaced by 1, 1 will be replaced by 0. Okay, so after replacing, after inverting the bits, this will be my 1's complement. Okay, this will be my 1's complement. Correct. So that's what we want to do in our next approach. Okay, but there is one condition. So we have either positive values or negative values. Okay, in signed data type. I'm talking about signed data type. Okay, so positive values we can have almost half of them. Negative values we'll have almost half of them. Okay, so for positive values, see, in this approach also, we don't have any issue with positive values. Okay, we don't have any issue with these values. Correct, they are correct in their place. We only have issue with these one. Okay, because of this duplicate 0, because of this duplicate 0. So what I can do, I can write them as it is. Okay, I can write them as it is. So for positive values, okay, write them as it is, and for negative value I will take 1's complement. Okay, I will take 1's complement, so I will store it in 1's complement. See, this is a depiction of how we can store values in the system. Okay, and we will see actually in actual how data is stored. So this is a depiction. I'm starting from unsigned, then signed, then 1's complement. Okay, and then we will see the final one. So let's see in 1's complement form. Okay, so I will write positive values as it is. So this will be 0, this will be 1, this will be 2, this will be 3, this will be 4, 5, 6, 7. Okay, till now I will store them as it is. Now if we have negative values, okay, how we can find that the value is negative or positive? Using MSB only. Okay, we are using almost similar approach as signed, but we are using 1's complement for negative. Okay, so just see the MSB. If our MSB is 0, that means we have positive numbers. Okay, so write the positive numbers, positive decimal equivalent. Okay, these are nothing but decimal numbers. Okay, now if our MSB is 1, that means we have negative values, so we will do 1's complement of it. Okay, do 1's complement. I'm writing here 1's complement from here. Okay, so how we can do 1's complement? Just invert the bits. If you invert the bits, this will be 0 triple 1. Okay, and this will be, what is that 0 triple 1? It is nothing but 7. Okay, and I will write minus sign. Now invert this bit, this will be 0 double 1 0. It is nothing but 6. Okay, and add minus sign. Here invert the bits, this will be 0 1 0 1. It is nothing but minus 5. Okay, write this 0 1 0 0. Okay, this will be 4, and write minus sign. Here this is nothing but double 0 double 1. It will be 3. Write the minus sign. Here it will be 0 0 1 0. This will be nothing but 2. Add minus sign to it. And here it will be 0 0 0 1. This will be 1. Add minus sign to it. Okay, and at the last it will be 0 0 0 0. So it will be nothing but 0. Okay, and 0 doesn't have any sign, right? So these are the 1's complement form. Okay, these are the numbers in 1's complement form. So till in positive we don't have any issue. Okay, in signed also, in positive we don't have any issue. But what was the issue here? See, I'm increasing my bit by 1. Okay, but the number is decreasing. Okay, So if I'm increasing, see here, I'm keep on increasing, I'm keeping on increasing, so the number is increasing. But in case of negative, in case of negative, the numbers are decreasing. By adding a number, the number is decreasing. That should not happen, right? In one's complement form, what is happening? The numbers are increasing. Okay, the numbers are increasing in downwards. Here also, I started with -1. I'm adding one bit. Okay, I'm adding one number. It will be -6, then -5, then -4, then -3, then -2, then -1. Okay, so it is also increasing. Here it is keep on increasing. Here also it is keeping on increasing. But still, still what the issue? We have two zeros. Okay, here also we have one zero. Here also we have another zero. So the issue is with zeros. The issue is with zeros. See, we have solved this problem. In signed, what was happening? That the numbers are keep on decreasing in negative. Okay, but here we are adding numbers, so it should be increasing. So it is increasing. Okay, it is increasing every time. But after increasing, at the end, we have duplicate zero here also and here also. So we need this will also not work, because we also want to this decrease the zero. Okay, we also want to only one zero. So then in the number line, this will be negative, then zero, then positive, like this. Okay, we should not have two zeros. So this will also not in use. Okay, we will not use them in memory. Now, what's the next approach? What's the next approach? So the next approach is nothing but 2's complement. Okay, 2's complement, using 2's complement. So what is 2's complement? Let's understand what is 2's complement. So let's take previous example only. Okay, let's say we have 1010. This is nothing but 10 in decimal. Okay, I want to take 2's complement of it. I want to take 2's complement of it. So there are multiple ways to take 2's complement of it. Okay, let me tell you the first way. The first way is take 1's complement. Okay, and add 1 in it. Add 1 in it. Okay, and we know how to take 1's complement. So let's take 1's complement. Okay, 1's complement of 1010 will be 0101. Okay, this is nothing but 1's complement, right? Now add 1 in it. Add 1 in it. Add 1. So 1 plus 1 will be 0. Okay, and 1 will be carry. 10 will be 1. Okay, and this will be carry will be 0. So this will be 1 and this will be 0. Okay, so this will be our 2's complement. This will be our 2's complement of 10. Okay, this is one way of taking 2's complement. First take 1's complement and add 1 in it. Okay, if you didn't understand this operation, just for now understand it like, if in bit manipulation we are adding 0 in 1, the resultant will be 1. If we are adding 1 in 1, the resultant will be 0 and there will be carry 1. Okay, and if we are adding 0 in 0, the resultant answer will be 0. Okay, and carry will be 0. Okay, and if you are adding 0 plus 1, this will be same as 1 and carry will be 0. Okay, as of now understand like this only. Okay, so if we are adding 1 in 1, the result will be 0 and carry will be 1. So in this case we have 1 plus 1, this will be 0 and carry will be 1. Okay, and then 1 plus 0, it will be 1 and carry will be 0. So 0 plus 1 will be 1, carry will be 0, 0 plus 0 will be 0. Okay, so this will be our 2's complement. This will be our 2's complement. So this is one way, take 1's complement and add 1 in it. Okay, that's how we take 2's complement. Now there is one more way. Okay, there is one more way. So the second way is, so let's take previous example only. Let's say we have 1010. Okay, so write all the bits until you find the first set bit. This is nothing but set bit. Okay, 1. So from LSB, from LSB, write all the bits until you find first set bit. Okay, so here write 0, here write 1. Okay, once once you found the 1, okay, after that invert the bits. Okay, after that invert the bits. So this will be 1 and this will be 0. Okay, this is nothing but 2's complement. Okay, it is same as previous one, right? So what is the second way? I am writing here. Okay, write all the bits until first set bit. Okay, set bit means 1. We call 1 as set bit. Okay, and after that, after that invert the bit. Okay, or I can say take 1's complement, invert the bit. Okay, this is nothing but take 1's complement. Okay, I hope you understood this way. This is nothing but find the first set bit. Okay, write same bits, and after that just invert the bits. Okay, take 2 3 examples, you will understand. Let's say I am taking this. Okay, I want to find 2's complement of it. 2's complement. So write 1. Okay, you found the first set bit. So after that invert the bits. This will be 000. As simple as that. Let's take one more example. Let's say we have 1001. Okay, so write the first set bit, write until the first set bit, and after that invert the bits. This is nothing but 2's complement. Simple. Let's take 0110. Okay, so write 0. Okay, write 1. You found the first set bit. After this, from LSB to MSB, we are checking from LSB to MSB. Okay, so write, invert the bits. So this will be 2's complement of it. Okay, so whatever way you are suitable with, use that way. Okay, so this is the 2's complement. Now how we will use this, 2's complement to store data? So for positive we don't need to do anything. Okay, we don't need to do anything, just write similar. Okay, just write as it is. And again we are using this MSB bit. Okay, so for 0, if MSB bit is 0, that means we have positive numbers, so write them as it is. Okay, but if MSB bit is 1, we need to convert this in 2's complement. Okay, so we need to convert this in 2's complement now. So from here I will take 2's complement. Okay, I will take 2's complement. So write it here. This will be 1000. Okay, so it will be nothing but -8. Take this 1001. So write 1 here. Okay, and invert all the bits. So this will be 7 and write minus. Okay, again take this, write 0 1, and after this invert the bit. This will be 1 0. So it will be -6. Okay, and after this in here write 1 and invert the bits. So this will be 1 0 1 0. It will be 5, add minus to it. Okay, similarly it will be 0 0 1 0. So this will be -4. After that write 1, and after it invert the bits. Okay, so it will be 1 0 0. So this will be -3. After this write 0 1, invert the bits. This will be 0 0. It will be -2. After that write 1 and invert the bit, 0 0 0. So it will be -1. Okay, so in 2's complement, in this representation we have 0 to 7. Okay, we have 0 to 7, and after this we have -8 to -1. So we have only single zero. Okay, so this 2's complement form is used to store in our system. Okay, this is used to store in our system. Okay, let's say if we take int a equals to -10. Okay, what will happen? See, in system it will be stored in 2's complement form. Okay, in system it will be stored in 2's complement form. So if we have positive it stores simply what is the binary conversion of it. It will be 1010. Okay, but to store -10, what will happen? It will first convert it in 2's complement. Okay, so if you convert 1010 in 2's complement, it will be 0110. Okay, and that, see, if here I am taking 4 bits only, but the representation will be until the size of int. Okay, so let's say int take 4 bytes. 4 byte means 4 into 8, that means 32 bits. Okay, so for 32 bits, the 4 bits will be this one, 1010. Okay, and rest will be 0000 like this. Okay, and when you take 2's complement of it, it will be like 1 1 1 1 1 1 and so on. Okay, like this. So the MSB will be 1 in case of negative and 0 in case of positive. Okay, so whatever the size of data type, according to that only the system will take care. Okay, but the concept is same. The MSB is responsible for checking whether the number is positive or negative. Okay, so positive will be have MSB 0 and negative number will have MSB 1. Okay, for signed numbers. Now we have seen the range, right? We have seen the range. Okay, so let me take a generalized form of it. Okay, so we have taken 4 bits. Let me write it here. So I was taking 4 bits. Okay, and for 4 bits the unsigned range was 2 raised to power 4. That means from 0 to 2 raised to power 4 minus 1. Okay, and if I'm taking signed one, or let me take 2's complement one. Okay, which we are using in 2's complement form. Okay, let's forget about the signed and the 1's complement form. So in 2's complement form, because the data is stored in 2's complement form. Okay, so in 2's complement form, the data was from, for 4 bits, the data was from -8 to +7. Okay, so it was nothing but 2 raised to power 4 minus 1. Okay, 2 raised to power 4 minus 1 minus 1. Okay, so if we generalize this for n bits, for unsigned, we will have 2 raised to power n numbers, that will be from 0 to 2 raised to power n minus 1. Okay, and for 2's complement form, we will have data from, for n bits, we will have minus 2 raised to power n minus 1 to 2 raised to power n minus 1 minus 1. Okay, so let me highlight this one and this one also. Okay, so for unsigned, this will be our range. For signed, okay, for signed data, this will be our range. Now when you see the chart of range for integer, float, character, okay, you can find this. Okay, you can find this. So if your int is taking, let's say, 4 bytes, okay, it is nothing but 4 into 8, 32 bits. Okay, so it will be from 2 raised to power n minus 1 to 2 raised to power n minus 1 minus 1. Okay, now you can calculate minus 2 raised to power 31 to 2 raised to power 31 minus 1. This will be your data for signed integer. Okay, and if you are taking unsigned, then it will be 0 to 2 raised to power 32 minus 1. Okay, so if we calculate this, that will be same as the range given in the chart. Okay, so now I hope now you can understand how the data is stored in our system. Okay, this table, you can take a screenshot or note, whatever you want. Okay, this is the depiction of how data is stored in our system. So for unsigned, it is clear that we can take from 0 to the number. Okay, the range, whatever range. For signed, we don't use this one, we don't use this one. Okay, for signed, we use this one, 2's complement. Okay, for signed, we use this one. So data is stored in this form in our system for signed numbers. Okay, I hope you understood it. Now, till now, what we have done, till now, we have seen how data is stored in decimal form. Okay, we have seen decimal to binary and binary to decimal. Okay, We have seen what is 1's complement. Okay, just invert the bits. We have seen what is 2's complement. Okay, 2's complement is nothing but 1's complement plus 1. Okay, so these are the basic ones. These are the basic ones. We have seen what is MSB and LSB. Okay, this we use very frequently, that reset the MSB bit. Okay, set bit means the bit is 1. So these are the terms which we use. Okay, so we have seen few terminologies on bits. Okay, but how we can perform operations on bits? So usually if I write 5 plus 2, what will the answer? 7. Okay, so here what we are doing, we are performing arithmetic operator. Okay, this is arithmetic operators. Similarly, we have bit operators. Okay, bitwise operators. So let's discuss them. So we have these bitwise operators. Okay, we have bitwise OR, we have bitwise AND, we have bitwise XOR, we have left shift operator, we have right shift operator, we have not operator. Okay, so bitwise operator is represented as this, and bitwise AND is represented as AND, bitwise OR is represented as this, left shift as right shift like this, not like this. Okay, so let's understand each of them one by one. Okay, so first, let's understand about bitwise OR. Bitwise OR. Okay, and it performs between two operands. Between two operands. Okay, and it says that if any of the if any of operand is 1, I hope you understand what is operand. Okay, if any of operand is 1, result will be 1. Okay, let's take some example. Let's say if I do 2 bitwise OR with 5. So I can write 2 like this, okay, and I can write 5 like this. See, till here I am writing only 4 bits, okay, but there can be a lot of bits. There can be a lot of bits depending on the data type which I am taking. Okay, as of now, for simplicity, I am taking only 4 bits. Now, perform bitwise OR. Okay, so 0 or 1. If there is any bit which is 1, we can take 1. Okay, so this will be 1. 1 or 0 will be 1. 0 bitwise OR will be 1. 0 bitwise OR 0 will be 0. Okay, so the resultant will be 1 plus 2 plus 4. It will be 7. Okay, so the bitwise OR of 2 and 5 will be 7. Let's take few more example. Let's say we have 3 or 5. Okay, so 3 can be written as like this, 5 can be written as like this. Okay, it will be 1, it will be 1, it will be 1, it will be 0. So again, the bitwise OR is 7. Okay, and if I do simple arithmetic operation, it will be 8. Okay, so both are different. Okay, both are different. So this is nothing but bitwise OR. Very simple, right? Bitwise OR. Now let's learn about next operator. So our next operator is bitwise AND. Bitwise AND. Okay, we write it as single AND. Okay, this is ampersand. We call it as ampersand. Okay, now if I take example, let's say 5 and 2. So convert it in decimal, sorry, binary. It will be 0, 1, 0, 1. And 2 can be written as 0, 0, 1, 0. Okay, and the symbol is ampersand. Now it says that if both are 1, if both operands are 1, then only result will be 1. Okay, so here 1 and 0 will be 0, 0, 1 will be 0, this will be 0, this will be 0. Okay, so the resultant of it will be 0. Let's take one more example. Let's say 5 and 3. So it will be 0, 1, 0, 1, and 3 can be written as like this. Okay, now 1 and 1 both are 1. If both are 1, then resultant will be 1. Okay, and this will be 0, this will be 0, this will be 0. So it will be 0, 0, 0. Okay, so in arithmetic operators, we were doing operations on the numbers, decimal numbers. Okay, internally it is also converted in bits and doing operations, but in bitwise operator, we perform operations like this on every bit of number. Okay, let's say if I store it in int and int take 4 bytes, then it will be stored in 32 bits. Okay, so 5 will be written as like 0 0 0 0 0 0, and then at the end this, so 28 zeros will be there and 4 bits are there. Okay, so in each bit the manipulation will be done. Okay, we will do the operation. Right, now let's move forward to third one. So third one is very important. Okay, we will do a lot of examples using this. So third one is XOR. Okay, XOR operator, we write it as this one. Okay, and if I write all the possibilities, okay, so using two operands we will have 0 0 0 1 1 0 1 1. Okay, it says that I remember this like same is 0, different pay 1, different pay 1. Okay, what does it means? If both are same, take it as 0. If both are same, take it as 0. Okay, if both operands are different, consider it as 1. Okay, otherwise there will be a lot of confusion. Okay, I remember like this only, same pay 0, different pay 1. Okay, so whenever you will see same, it will be 0, resultant will be 0. If both are different, then resultant will be 1. Right, so that's how I remember XOR. Now if you do perform operation, let's take the same examples only. Let's say 5 XOR 2. So 5 can be written as 0 1 0 1. Okay, and for simplicity I'm taking small examples. Okay, you can perform these operations on different examples. Okay, this will be 0 1 0. Okay, this is 5, this is 2. Now XOR, perform XOR. So this is different 1, this is different 1, this is different 1, this is same 0. Okay, so 5 XOR 2 will be nothing but 7. Correct. You can take more examples. Let's take 5 XOR 3. 0 1 0 1 0 0 1 1. Okay, now I hope now you are very comfortable with the bits. Okay, so 1 XOR same pay 0, different pay 1, same pay 0, different pay 1, it will be 6. Okay, you can perform this operation in any compiler. Okay, any C++ compiler, you will get the same results. Okay, now I hope you understood XOR also. So it also takes two operand and the resultant will be same pay 0, different pay 1. Okay, if both are same, the resultant will be 0. If both are different, then the resultant will be 1. Okay, in this also we'll perform operation on each bit. Okay, so now let's move forward. Now the next one is, we have covered bitwise OR, bitwise and XOR. Now fourth, let's take bitwise NOT. Okay, NOT, this is nothing but this one, we called it a tilde. Okay, tilde. So what it does, as the name suggests, not, it just inverts the bits. Okay, and we only have one operand. Okay, so let's say if I take 5 and if I want to find the not of 5, so let's take 5. 5 will be 0 1 0 1. Okay, and if I invert all the bits, so it will be 0 1 0 1. Okay, so this will be nothing but tilde of 5 will be nothing but 1 0 1 0. Okay, and if you convert this in decimal, you will get it. Okay, so if you convert it, this will be 8, this will be 2. Okay, it is nothing but 10. So not of 5 will be 10. Okay, and if you observe, we have seen something, invert the bits, we have seen this somewhere. Okay, we have seen this somewhere. So what is this? Nothing but 1's complement. Okay, 1's complement. So whenever, you can write it in note, Okay, note, you can find one's complement using tilde. This is nothing but tilde. Okay, not operator. So if you want to find the one's complement of 5, you can simply write this. If you want to find the one's complement of number, you can simply write this. This is one's complement. Okay, and similarly for 2's complement also we have something. For 2's complement, let me write the correct spelling. For 2's complement, we have something called as this negative sign. Okay, so if you want to find the 2's complement, you can simply write minus num. If you want to find 2's complement of any number, you can simply write minus num. Okay, so this you can do in dry run. Okay, take some examples, do dry run. Okay, so if you take the minus num, this will be nothing but 2's complement of it. Okay, so majorly if you take 2's complement of, let's say, 6, what it will be? Let's say 2's complement of 6. 6 is nothing but 4200. Okay, and if you take 2's complement of it, okay, so it will be nothing but 0101. Okay, so 1010 is the 2's complement of 6. Okay, so if you have given 1010, its MSB is 1, which means it is negative. So you will convert it in 2's complement. Okay, so 2's complement of 1010 will be nothing but 0110. Okay, it is same as 6, and you will write minus. Okay, so 2's complement, for 1's complement, you can simply use tilde operation. Okay, for 2's complement, you can simply use negative. Okay, you can remember this, or you can find out this. Okay, you can find out this by taking few examples. Now we have covered and, or, XOR, not. Now we are left with the left shift operator. Left shift operator. See, everything is whatever the name suggests. Okay, in bit manipulation, whatever the name suggests, that means only. So we have this left operator. Okay, left. Moving to left. So in this, we have two operands. Two operands. Okay, and what left shift does? So let's say I want to left shift 5 by 2. Okay, left shift 5 by 2. Okay, so this is 2 times only. This is 2 times only. Okay, so if this is one operand, first operand, and this is second operand. Okay, so it means that you want to shift 5 by 2 times. Okay, you want to shift 5 by 2 times. So write 5 in decimal, it will be 0101. Okay, and you want to shift it 2 times. What does it means? When you shift it 2 times, okay, when you shift it 2 times, so we add something. Okay, we shift these bits. We shift these bits by how many times the number is given. Okay, so let's take it in decimal. So it will be 0101. Okay, and I want to shift it 2 times. I want to shift it 2 times. So what does it means? We'll shift each bit by 2 place. We'll shift each bit by 2 place. Okay, so let's say we have this in 8 bits. Okay, so let's say we have 4 bits as 0. Okay, let's say I'm storing it in somewhere which have 8-bit size. Now if I left shift 2 times, if I left shift 2 times, left shift each bit by 2 times. Okay, if you shift one time, it will be here. Okay, so let me shift one time. If you shift one time, it will be, this one will be here, 0 will be here, 1 will be here, and 0 0 0. Okay, and 1 0 1 0 will be removed. Okay, so remove this 1 0. So we will have only 4 zeros. Okay, and at the end I am shifting by left, so here also we will have 1 0. Okay, so if you shift one time, it will be shifted one time towards left. Okay, now you are doing shifting for second time. Okay, again just left shift by 1. left shift by 1. So it will be 0 added here, 0 added here. Okay, it will be 1 0 1 0 0 0. Okay, because the size is 8 bits, so the leftmost, okay, the MSB, whatever MSB will be, it will be lost. Okay, it will be lost. So let's say if we had one here, if we had one here, okay, for first shift it will be lost. Okay, for second shift it will be move away. So let's say we have something like 1 1 1 1 1 1 1 0. Okay, and if you do left shift by one time, okay, left shift by one time, so just move it by one time. Okay, so at the end this one will move. Okay, so it will be lost. So after left shifting by one time, it will be 1 0 will be added, and we will just move it one time. Okay, like this. If you do it two times, so we will add one more 0. Okay, and rest will be moved by one place. Okay, if you do three times, so every time 1 0 will be padded on the right and on the left, or I can say I will use LSB and MSB. That will be better term. Okay, so I'm writing it here. On every left shift, on every left shift, 1 0. Okay, 1 0 will be added on LSB, on LSB, and MSB will be lost. Okay, because we are doing shifting by one place. We are doing shifting by one place. Okay, and shift every bit by one position towards left. Okay, towards left. Okay, so now let's take some example. Let's say we have 2. Okay, and I want to left shift by 1. So let's write 2. Okay, let's take 8 bits now. We have, let's say, 4 zeros. Okay, and 2 can be written as this one. Let's say 4 0. Okay, this can be written as 2 can be written as this one. Okay, now if you left shift by 1, what will happen? 1 0 will be padded on the LSB, and just left shift 0 1 0 0 0 0 0. Okay, now what's the value of it? What's the value of it? So it will be nothing but 1 2 4. Okay, it is nothing but 4. What if you left shift by 2 times? So just left shift by 1 also. Okay, left shift by 1. So this will be nothing but 0 0 0 and 1, and all rest are zeros. Okay, so every time my MSB will be lost and 1 0 will be added to LSB. Okay, and we will shift all these bits. Now this is nothing but what? 1 2 4 8. This is nothing but 8. Okay, so let's note this point. So every time on left shift, the number multiplies by 2. The number multiplies by 2. Okay, so if you do left shift 2 left shift 1, it will be 4. If you do 2 left shift 2, it will be 8. So 2 into 2 into 2, it is nothing but 8. Okay, let's take one more example. Let's say 3. You shift 3 by 2. Okay, so this will be 4 zeros, and 3 can be written as like this. Okay, 1 2 3. Right, we have 4 zeros and we have this. Okay, this is 0. Now if you shift it 2 times, what will happen? 2 zeros will be padded, and these 2 ones will be here, and left will be zeros. Okay, and what is this? This is 1 2 4 8. 8 4 12. Okay, so 3 into 2 into 2 is nothing but 6 into 2 equals to 12. Okay, so how many times you do left shift, those many times the number will be doubled. Okay, so this is nothing but we can simply write it as, okay, if you write it here, let's say I am shifting n by k times. Okay, I am shifting n by k times. So it can be written as n into 2 raised to power k. Okay, so if k is 0, let's say k is 0, we are not shifting. So it will be n into 2 raised to power k. It will be n into 2 raised to power 0 is equals to n into 1 equals to n only. Okay, so we can write this as n left shift k is equivalent to n into 2 raised to power k. Okay, so let's highlight it. So these basic operations, okay, these basic operations only will be used in future problems. So please understand this carefully. Okay, if you understand this, then bit manipulation will be very easy. I'm telling you, bit manipulation will be very easy. Okay, because every important point I'm telling you, every important point I'm telling you. Okay, so please take care of this. Okay, please take care of this. This will be very helpful in future problems. So we have covered left shift also. Okay, so one more left. Okay, one more is left. So we have right shift also. We have right shift operator also. Okay, so can you guess what it works? How is it works? Okay, can you guess? In right shift also we have two operands. We have two operands. Okay, and we written like this. So it is also can be written as n right shift k. Okay, so in the left shift operator, we were shifting our bits to left, but in right shift operator, we'll shift our bits to right. Okay, let's take one example. Let's say 5 only. Okay, we have misused 5 a lot. So this will be 0 0 0 0. Okay, 1 0 1, and this will be 0. Okay, this is nothing but 5. Now I want to right shift 5 by 2 times. Okay, that means I will shift all these bits by two places. Okay, all these bits by two places. So if you move, okay, if you don't understand like this, just do one by one. Okay, so first shift one time. If you shift one time, what will happen? This is our LSB and this is our MSB. Okay, same as left shift only, but the direction will change. The direction will change. Okay, now my LSB will disappear. So by one time, I am shifting by one time, my LSB will disappear and I will pad 0 on my MSB. Okay, so let's shift by one. So it will be come here, it will be 0, it will come here, it will be 1, and all rest will be 0. Okay, and now on MSB, pad 1 0. So we have this 4 and 4. Okay, so pad 1 0 on MSB. This 0, pad 1 0 on MSB. We have done it one time. Okay, now if we do it second time, what will happen? Again shift the bit by one. Okay, so it will be 1 0 0 0, all zeros, right? 7 zeros. We have 4 5 6 7 zeros. Okay, so on the MSB, one more 0 will be padded. Okay, one more 0 will be padded. Now if you have shifted by one, when you have shifted by one, what was the value? This is right. Let me raise this. Okay, so what is the value of this? It is nothing but 2. Correct. Now if you shifted one more time, if you shifted one more time, what is the value of this? What is the value of this? 1. Okay, if you shift one more time, if you shift one more time, so this will be disappear. So all will be zeros. Okay, and it will be nothing but 0 only. We have 4 zeros and 4 zeros. Okay, so in right shift, what is happening? In right shift, what is happening? Let me take it in a note. So we have 5. Okay, on one right shift, on one right shift, it became 2. We have 2. On one right shift, it became 1. We have 1. On one right shift, it became 0. So can you observe? Can you observe what is happening? Can you observe what is happening? So in this case, in the right shift, what is happening that every time your number is dividing by 2. Okay, so 5 divided by 2, 2, 2 divided by 2, 1, 1 divided by 2, 1 divided 2 will be 0. Correct. So if you write it n right shift k form, it is nothing but n divided by 2 raised to power k. Okay, we can write it in this form. Okay, you can note it somewhere. Please note it somewhere. Okay, so I hope you understood it. Why I'm writing this. See, when you're right shifting, okay, why it is working? Why it is working? So why in left shift the number is multiplying by 2, and why on right shift the number is dividing by 2? Okay, so let's see. So in binary, what is happening? The numbers are like 1, 2, 4, 8, 16, 32, 64, 128, like this. Okay, the numbers, whatever bits are there, let's say 10, 10, 10, 10, like this. So whatever bits are there, okay, we multiply like this only. Okay, we multiply like this only. So it will be 64 plus 16 plus 4 plus 1. Okay, so in bits, what is happening? By adding one more bit. Okay, so let's say if we have one bit, how many options we have? Two. Okay, if we have two bits, how many options we have? Four. If we have three bits, how many options we have? Eight. Okay, so by increasing a bit, the options are increasing in a multiple of 2. Okay, the options are increasing in a multiple of 2. So technically in left shift, what we are doing, we are basically increasing our bit. Okay, so let's say if this is given, it is nothing but 4, right? If you do left shift, what you are doing, you are pushing it one bit ahead. We are pushing it one bit ahead. Okay, so it was 4. Okay, if you're pushing it one more bit, so it becomes 1 0 0 0. Okay, so it becomes 8, right? And in right shift, what you are doing, you are basically decreasing one bit. Okay, so let's say we have given trip 4 ones. In right shift, if you are doing right shift, what is happening? This bit get lost. Okay, so we only have these only. We only have left with this. Okay, so this was how much? 1 2 4 8 15. Okay, this is what? 7. So 15 divided by 2 is nothing but 7 only. Okay, so technically in right shift, what we are doing, we are moving one bit on right. That means we are decreasing our bits. Okay, so till now our data was in 4 bits. Okay, but we are taking it in 3 bits. We are taking it 3 bits. Okay, because the MSB is replaced with 0. We are padding MSB with 0. Okay, so on right shift, basically we are reducing our bits. Okay, we are reducing our bits. In left shift, we are increasing the bits. Okay, so technically the number is keep on increasing on left shift and keep on decreasing on right shift. Okay, so I hope you understood it. Okay, let's see how many bits are there. So these were all the operators. We have covered this. Okay, we have covered all these operators. Okay, along with what is 1's complement, what is 2's complement. Okay, we have seen how unsigned and signed data is stored. We have seen why bits are important. Okay, so I hope this is more than enough for the first lecture, and we will start problem solving from next lecture, and we will use these concepts. Okay, so please take care of these concepts. Okay, please learn this, because these only we will use in next lectures. Okay, these and whatever I have written in notes. Okay, whatever I have written in note, that is very important. Okay, whatever I have highlighted, that is very important. And I hope you found this session helpful, and please give your feedback and review in comments. Okay, it is very required, so please give your feedback, what can be improved. Okay, and what can be better. And please take care of these concepts. Okay, so we'll see you in next lecture. Till then, bye bye, take care.